Why are data type declarations so important? What do you think would happen if we don't define data types correctly in C? Why is it so important to define them properly? Let's clarify this with an example. Imagine we want to divide two numbers and display the result. Pay attention closely to the following example. First, we include the standard input-output library in our code. For the first number, we define the variable num1 as an integer. For the second number, we also define num2 as an integer. The result of division will be stored in a third variable result of type float. Finally, we print this result. And what do you think the output will be? Wait, surprisingly, the result is 3. But why is that? We stored the result in a float variable which can hold decimal numbers. The issue is that both num1 and num2 are integers. When dividing two integers, the result is calculated using integer division. So the fractional part is discarded. Now, if we change num2 to float data type, will the result change? Yes. Now, dividing 10 by 3 will give us the expected decimal result with 6 digits of precision. It's important to understand that this mistake is typically not visible during compilation. Instead, it only appears during program execution, which can lead to increase and incorrect results. Properly defining variables helps us avoid such errors during runtime. If you'd like to learn more about this, feel free to leave a comment and I'll discuss it further in future videos. Is learning data types difficult? I don't think so. Let's explore the difference of data types in C. Data types in C are generally categorized into 3 categories: basic data types, derived data types, and user-defined data types. Number 1, basic data types. These include ints, floats, double, and char. Number 2, derived data types. These include arrays, pointers, and functions. Number 3, user-defined data types. These include structures, unions, and enumerations. In this video, we'll focus on basic data types. Why do data types vary across processors? What about data types in programming for different microcontrollers like AVR, ESP32, STM32, and Intel processors? Why does the amount of memory allocated to these data types differ across various microcontrollers? How can we resolve this? Intel processors come in 2 general types: 32-bit architecture like the x86 series and newer 64-bit architecture like x64 processors. The char data type is consistent. The char data type is consistent across all processors. Intel, STM32, ESP32, and AVR occupying 8 bits of memory. When it comes into the integers, we have 4 types: short, int, long, and long. The memory size of short is consistent across all processors at 16 bits. For int, on Intel x86 processors, it's 32 bits. But in x64 processors, it can be 32 or 64 bits depending on the operating system and compiler used. For example, in Eclipse IDE on a 64-bit Windows system, int data type is 32 bits. For STM32 and ESP32 microcontrollers, int data type is 32 bits, while for AVR it's 16 bits. For the long data type, it's 32 bits on x86 Intel processors, but 64 bits on x64 Intel processors. In all microcontrollers, long is 32 bits and long is consistently 64 bits across all processors. But how can we ensure the memory size of data types remain uniform across all processors? The solution is simple. The C standard library provides the stdint.h header file, which defines integer data types as an int 8_t, int 16_t, int 32_t, and int 64_t. These data types have the same memory size across all processors. For example, int 8_t is 8 bits, int 16_t is 16 bits, int 32_t is 32 bits, and int 64_t is 64 bits, no matter what processor we use. From now on, we'll use this header file to define integer variables. Comparing stdint.h with traditional C syntax. Would you like to compare the syntax of stdint.h with traditional C data types? Here's how they differ. The first column lists traditional C data types. The second column shows the standard C types, and the third column displays the types from the stdint.h library. The data types in stdint.h file are defined using typedef keyword based on traditional C data types. For instance, int 32_t starts with a U, indicating that it is unsigned. The int part signifies that it's an integer, and the t in the int 32_t indicates it's defined using typedef from standard C data types. Signed with unsigned integer types. When defining integer variables, we need to decide whether they will hold signed or unsigned values. An 8-bit integer can be positive negative, or 0. If we are sure that a variable will always hold non-negative values, we use unsigned char or uint underscore t. If we expect the variable to hold negative integers, we should use sign char or int h underscore t. The same approach applies to 16-bit, 32-bit, and 64-bit variables too. How big or small can data types get? You might wonder, how do we know how many bits should be allocated for an integer variable? Here's a table that shows the data types, how many bits they occupy, and the minimum and maximum values they can hold. We also provide the formula and decimal values for reference. In a previous video, we discussed how memory stores variables. Please check the link above. For example, an 8-bit variable occupies 1 byte of memory. An unsigned 8-bit variable can hold values from 0 to 2 to the power of n minus 1, where n equals 8. For signed variables, the last bit is used for the sign, reducing the total number of bits by 1. For a signed 8-bit variable, it can hold values from minus 2 to the power of n to 2 to the power of n minus 1 minus 1, where n is 8. This method of storing negative integers is known as two's complement, used across all processors, Intel, ARM, ESP32, and AVR. Floating point battle. Intel, STM32, ESP32, AVR. Who wins? What about data types that store decimal numbers? How are they defined? And how much memory do they take? Let's take a look at this in the context of Intel STM32 or ARM, ESP32, and AVR processors. Floating point numbers are stored according to the IEEE 754 standard. If you are interested in learning more about this standard, leave a comment and I explain it in future videos. Variables of type float use 4 bytes or 32 bits of memory across all processors, with a decimal precision of about 6 digits. The double data type use 8 bytes or 64 bits of memory except for AVR processors, where due to the lack of a floating point unit or FPU. In AVR, double data type is treated like a float in terms of memory. The long double data type uses 10 bytes or 80 bits. In Intel processor with an x86 architecture and 16 bytes or 128 bits in x64 architecture processors, providing precision of about 18 decimal places. In STM32 or ARM and ESP32 microcontrollers, the long double data type use memory and precision similar to double. Why not use double for everything? Why don't we use double for all data types to avoid mistakes? In microcontrollers, there are two main limitations. Limited RAM, for example, STM32 Cortex M series has just over 1 megabyte of RAM, and the slower processing speed of double data types. These limitations should be taken into account when programming microcontrollers. In our next video, we will discuss essential tips for choosing variable and macro names along with coding exercises in the Eclipse environment. Thank you for watching, and don't forget to leave a comment if you have any questions.